During your week 2 lab, a whole bunch of you recorded values that you measured with the multimeter on a 10K resistor and got numbers like 9800, 9770, stuff like that. And I'm really impressed that we managed to get so much data collected and that nobody messed up the spreadsheet. So with a little cleaning up, I was able to take this data and do some analysis. And now I'm going to lead you through the process I used to do that. I grabbed all of the stuff from there and Command C, copy that. And I'm a Mac guy, so I went and used my numbers spreadsheet and I pasted stuff into the table. Command V, and it took a little while. I've got it in there. I've got some problems because I've got a bunch of blank spaces here. So I resolved that by first I took just this column. Let's get rid of the labels so that we don't have to deal with them later on in Python. Now I'm going to take a portion of this down to there, and I'm going to move it. So I'll make this much smaller so I can actually just see the shape of it. And I'll grab the data from here and I'll copy it down to there. And then I'm going to grab this other chunk of it and copy it down to there. Whoops. Grab that piece and copy down to there. So I used my spreadsheet to help clean up this data, and now I'm going to get rid of all of the blanks by just sorting the data. So I'll go over to sort and I'll choose to sort on column A, and it's sorted it. So I've got all of the numbers in column A here, and then I've got a bunch of blanks down at the bottom left over from the sort. So I'll get rid of all of the blank rows. Delete those rows. And now I'm going to save this as a comma-separated value file. So you can see I've got all of these numbers. They're all in order now. And one thing I'm noticing is that there's some of these that are 9400 and some, and all the others are 9700 and bigger. So we'll have a look at that later on when we analyze the data. I'll choose File, Export to CSV, and if I follow that through, I'll wind up with a CSV file, which I've already done. So we'll now go and import that into Jupyter Notebooks. So if I'm trying to generate a new notebook, I'll choose New Python 3 Notebook. I get a blank notebook. I want to import a CSV file. So if I went to the resources segment, I've got this stuff about reading a CSV. And I've got this compact version, which I've already got open here. So this was stuff that I did to open a CSV file before. I'm going to copy that, and I'll paste it into my new untitled worksheet. So I've got that. And if I run that, well, I get an error because it didn't find that file. The file I actually want is the one that I saved, and that's resistors 2017.csv. So if I run that, looks like it worked. So what does A actually look like now that I've read it in? When I saved it out, it still had a bunch of blank columns, so it put all of those there. So I'm only interested in the stuff that's in column 0. So let's get some data as floating point numbers into a matrix called R. So R is going to be, well, it's a NumPy function, and I want to, as a floating point array, take the parts of A, only column 0 that I really want. So I'll take every row, that's the colon, but just comma 0 for taking the 0 column. And that worked, I think. What does R look like? It's a whole lot of numbers. Looks like about 100 and some. What's the shape of R? It's got 127 things in it. So I'll set n equal to the shape of R, and we only want the first thing in there. So bracket 0. And did n wind up being 127? Okay, good. So we're going to be using that n equal to 127 throughout this as we try to do some analysis. So now let's see what R looks like as a histogram. We'll plot a histogram of R. And there are the return values that came back from that. Well, that looks sort of like what we expected. It's punched in around 9,800 and some here, and there's those low ones. But maybe we want some more bins. So let's try it with 30 bins. Whoops, that's not the way I meant to type that. Bins equals 30. And so now we can see the shape a little bit better. There's the three values that were down around 9,400. There's another one up here at about 10,150. But most of it's soaked in right about there. So is this a Gaussian? Well, it's not really a Gaussian. It doesn't look quite symmetric. Besides, it's got these weird little outliers out here. So what might have been causing those outliers? Well, I came up with some explanations that might be the case. And I'm just going to copy over what I have written. And I'll make sure that that's a markdown window. And then when I run that markdown window, those three, what's going on? Well, if I look at it, they all came from group 209. So I think it's one outlier operation. And in terms of explanations, if they put another resistance in parallel with the resistor they were measuring, and it would have had to be about a 200 kilo ohm resistance in parallel to move it from here down to here, that's a possibility. And that might have been just that they were measuring it between their fingers and their fingers were wet. Because I tried to replicate that. I licked my fingers and measured a resistance through my body. I got about 1 mega ohm with them dry, but I was able to get down close to 200 kilo ohms with them moistened. And it was hot and humid when we did this stuff, so there might have been some moisture on their fingers. Alternately, group 209 might have been using a multimeter with a rundown battery. And I know that we replaced the battery in one of the meters on Tuesday or Wednesday. Or they might have got their resistors from a different manufacturing batch that actually had a different mean. This one's centered around 98.5. This one might have been actually a different batch. That's a possibility. And they're almost inside the 5% tolerance range. They're supposed to be 10K, so 9,500 would be 5% below 10K. So that's close. Or there could be some combination of effects there. So I'm not entirely sure I'm ready to throw these out of the data just yet. Let's keep them in, but keep in mind that they may be a little strange. So let's try plotting this as a normalized value as a PDF rather than as a count of frequencies, how many resistors fit in a particular bin. And I do that by setting the normalization to 1. And you see we get exactly the same shape, but now it's got a different scale over here. That's probability density. So let's try plotting a histogram with a Gaussian distribution, an equivalent Gaussian distribution. So I'll go back up here and I've plotted that histogram. Let's figure out what's going on with the equivalent Gaussian distribution. I'd like to go over this whole range, so I'll I'll create a linear space in resistance that goes from 9,400 up to 10,200 with 1,000 steps along the way, just so I can do some calculations. Then I'll create a Gaussian probability density function over that space, and I'm going to use that norm.pdf function that we've used before, and I'm going to go over the space R, and I'm going to use a PDF that's got a mean the same as the mean of our resistance values we measured, and a standard deviation the same as the standard deviation of those resistance values that we measured. So if I run that, that all ought to work, right? Oh, it doesn't know that norm PDF function. Well, here from our resources file, we had some stuff where we were looking at these Gaussian random functions, and we had imported this SciPy stats library, or at least part of it, the norm function. So I'm going to copy that and paste it in over here so that we've got that library loaded. Okay, so now we've succeeded in doing the calculation. We need to plot out the results and see if we can compare them. So I'm going to plot. What do I want to plot? I want to plot over R, and the thing I want to plot over R is P. And well, it's got the mean in about the right place, but these outliers here have sort of stretched out that orange distribution a little further than I might have liked. So let's try creating another one here. Let's create P1 and make it equal to norm.pdf of over R of a mean. Well, it's got to be a smaller mean. Looks like the mean, or rather it's got to be a mean's probably about the same. Let's call it 9,800. And a standard deviation, let's pick 50. And then I'll plot that one as well. Plot over R the values of P1. So I've got a green distribution here. It's narrower. So I've probably got my standard deviation close to right, but my mean is wrong. So maybe 9850. So I'm just eyeballing this now to get something semi-comparable. 9850. Oh, 9860 maybe. And a standard deviation of 50. That looks like a relatively good representation for the stuff in the middle here. So if we were trying to figure out what was going on with this distribution, I would guess that most of these resistances that we've got here have a mean around 9860, and that the standard deviation is about 50, or at least that's what we got with our measurements. But is that actually what's going on? I'm a little concerned here. If we wanted to make a statement about these resistors, we'd need to actually understand our measurement process. I'm fairly confident right now that I can say that these 10K resistors, they're all in spec. They're all within 5% of 10,000 ohms. But if I wanted to say more about them, I think I maybe need to simulate the process a little bit, because we already talked here about some of the things that might go wrong. So let's try a simulation. Let's assume that our actual resistor values are pretty close to 10K. So we'll create a set of actual resistances. Just in simulation, we're going to want 127 of them, just as if we measured them. And let's assume that they're 10,000, so they're all 10 kiloohms, plus some random variation. So we'll take a random number, and this is going to be a random number that's normally distributed, and we'll take n of them. Remember, n is going to be 127, and we'll multiply them times 10. So that's giving us some random actual resistances. And let's take some of this plotting stuff from up here just so that we've got a place to start. And we'll also plot a histogram for our actual resistances. And what do we get? Well, there's our random 127 resistances, all pretty tightly grouped around 10,000, and they're in a really different space than what we actually measured. But hang on, we measured with a multimeter that has some limited accuracy. So our uncertainty in our multimeter, the uncertainty in each resistance measurement is 2%. No, not 2%. I checked the spec sheet. 0.2%. 0.002% of full scale, or of the measurement that we're making. So let's multiply 10,000 by 0.2%. That's our uncertainty. So now we can simulate what we would have got from the measurement as the actual resistance plus some more random variations due to our uncertainty in our measurement. So we'll add another NP random number here. (127 random numbers), and we're going to scale that by the uncertainty in the resistance, and the uncertainty in the resistance would be 2 standard deviations, so we'll divide that by 2. And now I'll plot out, instead of our actual, I'll plot out our sim, or maybe in addition, I'll plot out our sim. So let's run that now. So I've got now this green distribution, which is a little wider than the orange distribution that I had. It's hard to see those. Let's make them partially transparent so we can see through them. So I'm going to make that alpha value equal to 0.5 so we can see halfway through it. And likewise, alpha equal to 0.5 here. So now we can sort of see the orange stuff through the green stuff and vice versa. So still pretty tightly grouped around 10,000. Still noticeably different from this one. And you'll learn some statistical tests to actually prove this later. But just looking at it, we can see that those are 2 different populations. But let's consider the possibility that in addition to this, we had some parallel values happening. Everybody had fingers that were a little bit wet. So now we'll introduce the idea that the resistance of the finger on each measurement also existed, and it was somewhere around, well, let's say 800,000. So almost 1 megohm, but it varied randomly around that. And it was normally distributed again. And we need 127 of those values. And let's assume the standard deviation was, say, around 200,000. Well, the resistance of the fingers would go in parallel with the resistance actual to change the value. So the resistance of the simulated value with the finger involved, whoops, so let's call that R sim with a finger getting in the way. It'll be 1 over R sim plus 1 over R finger. That'll be the resistance that we get overall. So let's calculate that and plot it out as well. So now we'll plot out the resistance simulated with a finger and see what we get. Calculates through, and sure enough, the original values were all pretty closely grouped around 10,000, but if we had some fingers getting in there and providing a little resistance in parallel, we've got this distribution going on, the pink versus the blue. I'm pretty confident that these two are different from the blue one. I don't know that that one is different from the blue one. So at this point, having thought about how I made these measurements, or how you made these measurements, I'm not entirely sure that we can say anything more about our resistors other than they're 10K resistors and they're within the 5% specification. If I really wanted to nail it down, I'd have to make sure I did a more careful experiment, because I've already figured out a couple of things that could lead to not quite the results that we expected when we sat down with our measurement systems. So every time you introduce a factor in your measurement, it's going to alter your uncertainty and alter your measurement, and it may do it in a biased way, like putting that resistance of the body in parallel. So go and have a look at the full worksheet that I've done. It's called Resistance Measures. That's what I saved my original as. And you can play around with these values. For instance, suppose we said that there was more variation here. We had standard deviation of 300,000 ohms on the resistance of people's fingers. I could run that, and it's spread out even closer to the blue values. So by simulating what you did in the measurements, you can simulate the effects of different things you think might have changed your results and see how they would have changed the results. And that can be really useful.